Today, we are tackling a fundamental question. Why is the normal distribution, often called the bell curve, so ubiquitous in nature and statistics? And more importantly, how can we derive it from first principles?
That's a great question, Dr. Akira. I've always seen the normal distribution everywhere, but I've never really understood why it appeared so frequently. I'm excited to dive into this how.
Excellent, Hassan. Our journey today will take us through the maximum entropy principle. Again, imagine you have a continuous random variable, let's call it x, which maps outcomes from some sample space omega to real numbers. We know two things about this variable: its mean, mu, and its variance, v. Our goal is to find the probability density function rho x of x that describes this variable.
So, we know the mean and variance, and we want to find the most unbiased or least assumed probability distribution that fits those facts. Is that where the maximum entropy principle comes in?
Precisely. The maximum entropy principle states that, given some testable information about a probability distribution, the most appropriate distribution is the one that maximizes entropy. It's about choosing the distribution that makes the fewest assumption beyond the given data.
And what exactly is entropy in this context?
For a continuous probability density rho of x, the entropy S of rho is defined as a functional. That is this. It's a measure of uncertainty or randomness. A higher entropy means more uncertainty.
Okay, so we want to maximize this S of rho, but we have those two pieces of information you mentioned, the mean and the variance. Are those our constraints?
Exactly. We have three constraints actually. First, the probability density must be normalized, meaning the total probability over all possible outcomes must be 1. That is this. Second, the mean is given by this equation. And third, the variance is defined by this equation. We assume these constants mu and v are known constants.
So, it's a constraint maximization problem. How do we solve that? With Lagrange multipliers?
You are on the right track, Hassan. Since rho of x is a function, not just a simple variable, we need to use functional differentiation. We define the Lagrangian L of rho by incorporating our constraints with Lagrange multipliers alpha, beta, and gamma. Notice the gamma over 2 term. This is a common convention when dealing with variance constraints, and it simplifies the algebra a little bit later on.
Functional differentiation sounds a bit intimidating. How does that work?
It's similar to regular differentiation, but instead of varying a variable, we vary the function itself by an infinitesimal amount. Let's imagine we change our density slightly from rho of x to rho of x plus delta rho of x. The Lagrangian then becomes L of rho plus delta rho, which is this. Our goal is to find the difference, delta L of rho, which is equal to L of rho plus delta rho minus L of rho. At the local maximum, this difference delta L must be 0 for any arbitrary infinitesimal change delta rho.
Okay, so we are looking for where the slope of the functional is 0, just like finding a maximum in regular calculus.
Exactly. Now, let's look at the first term in the Lagrangian, the entropy term. We have rho plus delta rho times log of rho plus delta rho. We can use the Taylor approximation for log of 1 plus x, which is approximated by x, when the absolute value of x is much less than 1. So, log rho of delta rho becomes log of delta times 1 plus delta rho over rho, which is equal to log rho plus log 1 plus delta rho over rho, which becomes log rho plus delta rho over rho. Substituting this back, we get this. Expanding this, we get this expression. Ignoring terms of order delta rho squared or higher, this simplifies to this. So rho log rho plus delta rho times log rho.
So, the change in the entropy terms is approximately this.
Precisely. And if you go through all the terms in the Lagrangian, you'll find that the difference delta L of rho simplifies beautifully to this. For delta L to be 0 for any arbitrary delta rho, the term in the square brackets must be 0. This gives us the functional derivative, that is, this.
So this is the crucial step. We found an expression for rho of x.
Indeed, solving for rho of x, we get rho of x is equal to this. We can combine the constant terms into a single constant c and then rearrange the exponent by completing the square for the x terms. We get rho of x is equal to c times exponential of this, where c is a new constant.
So it already looks a lot like a Gaussian. Now we just need to figure out what c, beta, and gamma are using our constraints.
Exactly. Let's start with the normalization constraint, that is this. Substituting our expression for rho, we get this. This is a Gaussian integral. We know that the integral of exponential of negative ax squared over the entire real axis is square root of pi over a. In our case, a is gamma over 2. So the integral evaluates to c times square root of 2 pi over gamma. Therefore we have c times square root of 2 pi over gamma equals 1. Solving for c, we get c is equal to square root of gamma over 2 pi. So our density function now looks like this.
Great! One constant down. What's next? The mean constraint?
Yes, the mean constraint is this. So let's make a substitution to simplify the integral. Let y equal to x minus mu minus beta over gamma. Then x is equal to y plus mu minus beta over gamma. The integral becomes mu is equal to this. We can split this into two integrals. First part containing y here, and the second part containing only the exponential part. The first integral is an integral of an odd function over a symmetric interval, so it evaluates to 0. The second integral is just a normalization integral we just solved, which is square root of 2 pi over gamma. So we are left with this, which simplifies to mu equals mu minus beta over gamma.
And for this to be true, it must mean that beta over gamma is 0, which implies beta is 0 since gamma cannot be 0.
Exactly. So beta is equal to 0. This simplifies our density function even further, like this.
One last constraint, the variance.
Indeed, the variance constraint is this. Substitute the current form of rho of x, we have this expression. Let z equal x minus mu, then dz is dx. The integral becomes this. This is another standard Gaussian integral. We know that the integral of x squared times exponential of negative ax squared over the entire real axis is 1 over 2a times square root of pi over a. In our case, again, a is equal to gamma over 2. So the integral evaluates to this. Therefore, we have v is equal to this. Simplifying this, we get v is equal to 1 over gamma.
So gamma is 1 over v. That's it. We have all the Lagrange multipliers.
Precisely. Substituting gamma equals 1 over v back into our expression for rho of x, we have this, which simplifies to rho of x equals to 1 over square root of 2 pi v times exponential of negative x minus mu squared over 2v.
Wow! That's the probability density function for the univariate normal distribution. So by maximizing entropy subject to knowing only the mean and variance, we naturally arrive at the Gaussian distribution. That's incredibly elegant.
It is, isn't it? This derivation shows us that the normal distribution isn't just a convenient mathematical tool. It's the most honest or least opinionated distribution when all we know are its first two moments. It assumes nothing more than what's given. This is why it appears so often in natural phenomena, where countless small independent random effects often sum up to produce a normal distribution, a concept known as the central limit theorem.
That makes so much sense now. The maximum entropy principle provides a really powerful way to understand why certain distributions are fundamental. Thank you, Dr. Akira. This was incredibly insightful.
My pleasure, Hasan, and thank you. And thank you for watching. If you have any questions or comments, please write it in the comment section below. And if you like this video, please hit the like button and don't forget to subscribe to this channel. See you in the next video. Bye.